Hi, everybody. This is Lauren Nichols. I'm the Technical Manager with the American Carbon Registry, and I want to welcome you to this webinar about a new ACR methodology and development for quantifying greenhouse gas emissions reductions from wetland implementation and rice cultivation in California. The methodology development is a collaborative effort of the Sacramento-San Delta Conservancy, the California Coastal Conservancy, the California Department of Water Resources, the Nature Conservancy, HydroFocus, and Tierra Resources. And funding for the development was provided by the Sacramento Municipal Utility District, the California Coastal Conservancy, and the Metropolitan Water District, and DWR, the Department of Water Resources. We're really fortunate to have two of the methodology authors, Dr. Stephen Deverel of HydroFocus and Dr. Patricia Oikawa from UC Berkeley, presenting with us today as well. And I just am going to go through the agenda really quickly, a very simple agenda. I'm going to do an introduction and provide a brief background on Winrock and ACR. Then I'll hand it off to Steve and Patty, who are going to cover the details of the methodology itself, all of the baseline and project quantification and model details involved in it. So, and then finally, we're going to close the whole presentation with enough time for question and answers. I'm going to just do a little bit about the webinar logistics. In your webinar pane, you should see near the bottom, there's a chat box in which you can submit your questions at any point during the presentation. So just type those into that chat box, and if you can, include your name and organization as well. During the Q&A period at the end, we'll direct the questions to the appropriate presenter. In the event that we do not get through all the questions that we receive, we will do our best to respond to any questions not addressed via email or other follow-up by phone call as we can after the presentation ends. I also want to point out that this methodology is currently open for public comment through February 12th. So part of the purpose, of course, of this webinar is educational, but it's also an opportunity to get feedback on the new methodology, and we will take any questions and answers that are covered during this webinar and include them in the public comment documentation posted alongside the methodology on our website. So if you would like to provide other comments or ask additional questions, beyond what is feasible in this format, you can certainly feel free to go to the ACR website where the public comment draft of the methodology is and submit your comments. There's an ACR email address there that you can send those through. And finally, I just wanted to point out that the webinar today will be recorded, and both the audio recording and the slides will be made available to all the registrants. Okay, so just a quick overview of, or a little bit of a background on Winrock. The Winrock International Institute for Agricultural Development, which is the parent nonprofit organization of the American Carbon Registry, has the following general mission statement. Winrock works globally in about 60 countries now with around 1,000 staff. With the mission to empower the disadvantaged, increase economic opportunity, and sustain natural resources. Winrock was formed in 1985 from the merger of three predecessor organizations that were all Rockefeller family organizations devoted to international development, agricultural development, and food security. It is headquartered in Little Rock, Arkansas, and Winrock is short for Winthrop Rockefeller, who left the East Coast, moved to Arkansas, and began raising cattle. And you can see his photo right there on the bottom corner of the screen. The organization as a whole is very focused on climate change and its impacts, particularly on disadvantaged communities. We believe that as climate change progresses, so that has been a focus for Winrock in many years, and many of the programs Winrock supports in clean energy, forestry, and natural resource management, including the American Carbon Registry itself, are geared towards trying to respond to that issue. We also believe that markets are an effective path to mobilize action in this area. Okay, so going to the American Carbon Registry, ACR was founded almost 20 years ago now as the first U.S. private voluntary carbon registry, and since then we've registered upwards of 55 million metric tons of credits across a wide variety of project types. The registry ended up joining Winrock International in 2007. And here's just a really quick overview of the main roles of the registry. One is to develop and approve carbon methodologies, as we're talking about today. We develop some new methodologies in-house, and others are brought to us from external authors, but all are put through a rigorous review process, including a public comment period and scientific peer review process. We also review projects which are developed against the approved methodologies, and the projects are then validated and verified by accredited independent third-party auditors. Finally, the registry platform transparently tracks the credits resulting from these projects and their associated transactions and retirements. ACR was approved by the California Air Resources Board in 2012 as an offset project registry and early action offset program, meaning that projects developed under the ACR approved offset protocols, as well as those developed using the ARB recognized early action protocols, can come to ACR to be listed, go through the verification process, and then be issued registry offset credits that are eligible to be converted into ARB offset credits and used by the regulated entities in California cap and trade market. Our California offset program is based out of ACR's Sacramento office. Okay, so going into the topic of today, so why wetlands? Well, Winrock is very focused on supporting activities that improve resource management and support healthy and productive land-based systems, and in ways that obviously will benefit the environment, but also increase resilience and ecosystem services that are beneficial to the populations around them. So some of these overarching benefits, key benefits are listed here, which include the tremendous potential to sequester carbon and avoid emissions from wetland loss, the benefits to wildlife habitat, water quality, storm surge protection, and considering wetlands to be soft infrastructure to protect quote-unquote hard infrastructure. So as some of you know, ACR has an approved wetlands methodology for restoration of deltaic or degraded deltaic wetlands in the Mississippi Delta. And at the time of development for that methodology, it was recognized that there's a significant replication potential in the US and across the globe. And the intention was always to build upon the existing model that that methodology provided and integrate region-specific restoration techniques and data from other geographic areas, so which is exactly what this new methodology set out to do for the unique cases of wetlands in California. All right, so I will wrap up there and pass it on to Steve Deverel of HydroFocus to continue with the details of the methodology itself.
Thank you, Lauren. Good morning, everyone. I'm going to talk for a few minutes here about our methodology for quantifying greenhouse gas emissions reductions through wetland implementation and rice cultivation in the Sacramento-San Joaquin Delta, San Francisco Estuary, and the California coast. Just in the way of an overview, I can get to the next slide here. There we go. I'm going to talk a little bit about the geography, where this methodology is applicable, talk about the background, how this methodology evolved, and some of the underpinnings in terms of baseline carbon emissions, then get into the methodology itself, talk first about the framework, project and baseline modules, and then methods. I'm at that point going to turn it over to Patty Oikawa, and she's going to talk about a wetland model that she's been working on and is currently in the process of publishing. And then I'll come back and talk about the steps that are outlined in the framework module and walk through an example project and how those steps would actually look as the methodology would be implemented. So just to talk first about the key area of geographic applicability, it's really a methodology that promotes projects that include rice cultivation on organic soils, development of managed wetlands on subsided lands, and tidal wetlands. So it would include the California coast. San Francisco Estuary is really the main area of interest and one of the areas that really prompted the development of methodology. A key part of it is the delta, which is the area where the two main rivers in California come together to flow out through Sassoon Marsh and into the Pacific Ocean. And Sassoon Marsh is another possible area of application of the methodology. And really it's areas where we have organic soils that are either seasonally drained or drained perennially that can oxidize and emit carbon dioxide. And so that's the primary area for application of the managed wetlands. Managed wetlands would be below sea level on subsided lands. And then in the San Francisco Bay, we have areas in the South Bay that are, for example, open water, former salt ponds and such that are being converted to tidal wetlands, which are also possible areas for implementation of the methodology, as well as other areas on the coast that could be upgraded or converted to tidal wetlands. So in the way of background, talk a little bit about really a key area for where we see the methodology being applied, and that's where we've had extensive subsidence and greenhouse gas emissions in the Sacramento-San Joaquin Delta. It's an area of about 200,000 acres where there are organic soils, and there has been substantial subsidence over time. This was an area prior to development of freshwater tidal marsh. There was accretion with sea level rise of the marsh platform, and of course under anaerobic conditions there was basically this accretion of biomass over time. The estimates are that about 5 billion cubic meters of organic soils accumulated during the last 6,000 to 7,000 years, and about half of that has disappeared due to draining of these soils for agriculture. We now being exposed to oxygen, they're microbially oxidized at a fairly rapid rate. There's also been wind erosion and burning over time, and there is a component of compaction as well. So we see elevations in that area, in the Sacramento-San Joaquin Delta, that are as much as 7 to 8 meters in some cases. Much of the central delta, where we have had the most subsidence, is 5 to 6 meters below sea level, and then around the periphery where there's been less subsidence, we have higher elevations. But most of this area that's encompassed by the orange colors is below sea level. Another area is the San Francisco Bay area, or Sassoon Marsh. Much of these dark blue areas are also organic soils that currently are seasonally flooded during the winter, but drained during the summer, where there's ongoing oxidation. And so we have had subsidence, for example, in Sassoon Marsh, and emissions of greenhouse gas in these subsided and oxidizing soils. We don't have a lot of data in the Sassoon Marsh. We do have a fair amount of data for the Sacramento-San Joaquin Delta, but not a lot of data in terms of greenhouse gas emissions in Sassoon Bay. So we've used a methodology framework. I should say that we benefited substantially from the Louisiana protocol that Lauren mentioned. Sarah Mack actually worked with us on the writing team to help write this methodology and provided substantial important input. It's a modular framework. So here's the basic modular structure. We have a wetland rice cultivation methodology framework. It describes the structure, function of modules, applicability, activities, requirements, and defines the geography. The baseline modules include the agricultural, seasonal wetlands, and open water baselines. The project modules include the tidal wetlands, managed non-tidal wetlands, and rice on organic soils. Methods and model modules are used for estimation of carbon stocks and emissions, and this includes the use of biogeochemical models, as Patty will talk about a little bit later. There's an uncertainty module that feeds into the estimation of baseline emissions as well as project greenhouse gas reductions. There are tools that are part of the package as well. These are existing tools available through ACR, risk analysis, significance, and plots, which basically helps decide how many samples are needed for collection of data. And then we've done a leakage analysis that would be part of the steps that I'll talk about later. I'll talk a little bit about the leakage analysis that we've conducted as part of this methodology development. This gives you more of a schematic of what lines up with what in terms of the baseline and project activities. So we have an agricultural baseline, which is primarily directed towards the Sacramento-San Joaquin Delta, although it could include other agricultural areas in the San Francisco Estuary. It's really for agriculture on organic soils. There's a seasonal wetlands component, which I mentioned earlier, which can include the Sacramento-San Joaquin Delta as well as Sassoon Marsh and other areas of the estuary, and then the open water baseline, which really, in terms of our thinking at the time, it was mainly directed towards the open water areas in South San Francisco Bay, but it could include other areas as well. So rice cultivation is strictly related to the agricultural baseline. Managed wetlands can be implemented from the agricultural baseline, as well as the seasonal wetlands. And then the tidal wetlands could also be implemented from seasonal wetlands and from open water baselines. These are some relevant land use examples and greenhouse gas relevancy from a baseline perspective. So for agriculture, the agricultural baseline, it's really primarily farming on organic soils on Delta Islands, could include other areas, but this is the main area. The primary greenhouse gas impact is greenhouse gas emissions, or CO2, nitrous oxide, and some methane emissions due to oxidation of organic soils. The agricultural fallow seasonal wetlands, fallow areas that have become impractical to farm due to excessive wetness in the Sacramento-San Joaquin Delta. Seasonal wetlands include the Sassoon Marsh area, as well as other areas in the San Francisco Estuary. And then the open water is primarily subsided salt ponds in the South San Francisco Bay, and there are open water areas in the Sacramento-San Joaquin Delta as well. And in all cases, this is the greenhouse gas emission in baseline is due to the oxidation of organic soils, and we don't really know about open water at this point. There may be a net greenhouse gas emissions, but there's no data. To talk a little bit about the example projects, So we actually have some managed non-tidal wetlands in the Sacramento-San Joaquin Delta on state-owned islands. This is Sherman and Twitchell Islands. There's generally a net greenhouse gas removal. There's an increase in soil carbon, and there are methane emissions as well. There are saline brackish tidal wetlands that have been implemented. One could read more about those in Callaway and others, which is cited on this slide. Rush Ranch and Sassoon Marsh is one example. And there's a net greenhouse gas removal where there is minimal methane emitted because of the salinity. And then rice is something that has been implemented to a certain extent in the Delta. There's about 3,000 to 5,000 acres of rice on various islands that are listed here. And for this methodology and this project module or project implementation, as well as the managed non-tidal wetlands, one of the big greenhouse gas benefits is the stopping of the ongoing emissions. So rice contributes to that by keeping the soil saturated during the warmest times of the year. And this kind of diagrammatically illustrates the two extremes, really. Drained cropland, which takes up CO2 in the plants, but also emits substantial amounts of CO2 during the oxidation. Due to the oxidation of these organic soils, there's some methane emissions. In restored wetlands, there's a substantial CO2 sink. Basically, there's a minimal CO2 emissions because the oxygen is now gone. It's an anaerobic system, and there is some methane emitted. So let me talk a little bit about the methods. This diagrammatically illustrates the activities and the associated methodological options for estimating soil carbon stock changes and emissions. So really, most of these have similar components. For all of them, we allow the use of biogeochemical models. In the case of agriculture, there has been eddy covariance data collected in the Delta, and so in combination with that, the harvested biomass needs to be quantified. We've developed a peer-reviewed subcalc model which predicts subsidence as well as CO2 loss for Delta organic soils. That's described in the methodology as well. And then one could also use subsidence estimates to estimate how much CO2 is lost from current baseline agricultural conditions. In open water, these three methods, the eddy covariance, chamber measurements, and biogeochemical model could be used. And for seasonal wetlands, similarly, eddy covariance and our chamber measurements for looking at CO2, methane, and possibly nitrous oxide could be used. And again, biogeochemical models and subsidence estimates. For the rice cultivation, again, the harvested biomass is important, and eddy covariance has been used in rice cultivation in the Sacramento-San Joaquin Delta. The biogeochemical model that Patty will talk about could also be used for that, and there's some lookup tables for estimating nitrous oxide emissions from rice cultivation in the Delta that are in the methodology. Chamber measurements could also be used to measure methane and nitrous oxide. Managed non-tidal wetlands, eddy covariance has been used in a number of wetlands in the Sacramento-San Joaquin Delta. The traditional method of using feldspar markers, soil coring, and sedimentation erosion tables, of course, is applicable, and the biogeochemical model and lookup tables are also options. And then the tidal wetland, there's an important part of it that's unique to this particular project, which is fluvial carbon loss or gain in combination with eddy covariance, feldspar markers, soil coring, could also be and has been used. The Callaway and others paper describes the use of these techniques, and then the biochemical model could also be used. So I'm going to turn it over to Patty Oikawa at this point, and she's going to talk about the Wetlands Model, peatland ecosystem photosynthesis respiration methane transport model that's been used and calibrated for the Twitchell Island wetland in Sacramento-San Joaquin Delta.
Okay, great. Thank you, Steve. Yeah, so I'm going to spend just a little bit of time now introducing you all to this model that can be used in restored wetlands. And this simulates exchange of carbon dioxide and methane from the wetland, so you can account for the entire greenhouse gas budget. And then also I want to familiarize you with the types of data that are needed to run the model, and then finish up with some of the model performance statistics. So basically how well you can expect this model to perform in a restored wetland. So this is just a conceptual diagram of the model showing the major processes that are simulated and the pools that are simulated. Try and advance to the next slide. Okay, sorry. I might have advanced too many slides. Okay, so this first slide is showing, I'm just going to start walking through now the main processes that are simulated in the model, starting out with photosynthesis or gross primary productivity of the restored wetland. So this is just how much carbon is being taken up by your plants in any given wetland. And we predict photosynthesis using a really simple light use efficiency model, and the equation is provided at the bottom of the slide here. But the main inputs that you need for this part of the model is our radiation, temperature, and leaf area index. And radiation and temperature are both very easy data to come by. You can just pull them from a local weather station, for example. Leaf area index is just the amount of photosynthesizing tissue you have per square meter, and it's really important for scaling up photosynthesis. And it's actually, the model is very sensitive to that parameter, so I wanted to spend just a little bit of time talking about how you could estimate leaf area index at your restored wetland. So we discussed in the methodology a few different ways of going about doing that, but one of the best ways that we've found with our work is using digital cameras. So these are just a really simple, basic camera that's mounted above the wetland. It takes photos every day, and from the greenness of the image, you can infer, using this empirical function, what your leaf area index is at your wetland on any given day. There's also remote sensing products that can be used to infer leaf area index, and we go into that in the methodology. And then, of course, destructive sampling, where you actually physically go out and sample your leaf area index. Of course, that takes, that's pretty labor intensive. And then the next slide, okay, so the next main process is ecosystem respiration. So how much CO2 is being released from the wetland to the atmosphere, and this is from both plant and soil. And this we simulate using Michaelis-Menten equations, simulating a couple of different carbon pools here. But the main inputs for this part of the model are initial soil organic carbon content for the wetland, and then also water table height. And actually, in our analyses, we found that the model is very insensitive to that initial soil organic carbon content. So a great option for that is using carbon maps that we have for the delta. Water table height's really important if the water table is fluctuating quite a bit, but if it's a managed water table with very stable conditions, it's not something that you need to measure all the time, but we go into that in the methodology as well. Okay, and then to simulate methanogenesis and methane oxidation in the wetland, we're using a really similar approach here, again with Michaelis-Menten equations with the same types of inputs that we're using to simulate CO2 production. And then finally, we simulate methane transport to the atmosphere through both plants and directly from the water surface. And for this part of the model, there's no unique inputs that I haven't already discussed. And these are both gradient-based fluxes. So basically, how much methane you have stored in your system versus how much methane is in the atmosphere is really driving those fluxes. And I'm happy to go, and if you guys have any more detailed questions about these equations that I've been running through really quickly, I'm happy to answer questions. And also, if you want to contact me later, I'm happy to go into more details of how the model works. So the model was developed and has been validated and tested in the West Pond wetland, which is on Twitchell Island. And this is a restored, managed wetland, freshwater wetland that was established in 1997 by the U.S. Geological Survey and also the Department of Water Resources in California. And this is on an island that's sort of on the western edge of the delta here. It mostly has tules and has some cattails also, but it's a very mature and densely vegetated wetland. You can see in the photos here on the left. Has a very distinct phenology as well, so you have a very strong growing season in the summer with lots of dense green vegetation, and then in the wintertime we have a fully senescent canopy. That's common in what you would expect in a restored wetland in the delta. So the model was parameterized and validated using data that we collected in that wetland. So here on the left is showing all the inputs that you need to run the model, which I already went over with you. There's 5 in total. And again, we actually measured all of these at our site, but if you were running your own project, you can pull some of these data from weather stations and remote sensing, or etc. And then to validate the model, we needed measurements of ecosystem exchange of CO2 and methane. Those are the important greenhouse gases for restored wetland systems. So we had an eddy covariance tower running at the site for multiple years, and we used those data to parameterize and validate the model. This wetland is also a great site for developing the model because it has been so well studied for a very long time. So we actually also used some historical soil accretion measurements that were taken at this wetland from the beginning, from 1997 up to 2005. Okay, so now I'm going to go into some of the data and the model performance statistics for this West Pond wetland. On the top panel here, we're showing that net ecosystem exchange of carbon dioxide over time. And this is in grams carbon per meter squared per day. And it starts around August 2012 and runs to the end of 2014. That's when we had our tower first set up in the wetland. And the black dots here are the eddy covariance data. So those are measured. And then the model is in gray with 90% confidence intervals. And negative numbers mean that you're sequestering carbon dioxide, so the wetland is taking CO2 out of the atmosphere and storing it in the system. So you can see during the growing season you have a strong net uptake of carbon dioxide, whereas in the wintertime we have a totally senescent canopy with slightly positive fluxes, which means release of carbon dioxide to the atmosphere. You can see the model is tracking the data very well. And this big black line in the middle is just indicating to you all that all the data to the left of the line were used to train the model, and all the data to the right of the line were used to validate the model. So that's really when you're testing the model and seeing how well it can perform, and that was a full year of eddy covariance data of 2014. And on the bottom, I'm showing our measurements of water table height. And you can see that most of the time, this is a managed water table, and it's mostly managed at 25 centimeters above the soil surface. But as I mentioned before, we had a highly variable water table, especially during the summer of 2013. So this ended up being a pretty important measured input, at least for this system. In the next slide, I'm showing some of the performance statistics for the model. So we're explaining about 90% of the variance in flux that we observed. And then you can see on this right upper graph, cumulative NEE over time. So that's cumulative CO2 uptake by the system over all of the years that we've been observing. So you can see there's a clear uptake or negative flux of CO2 into the system over time, with the observations in black with 90% confidence intervals, and the gray is the model. And so really importantly is that validation period of the 2014 data where we ran the model forward, and that can give us a sense of how well we can expect it to perform. And it overestimated uptake of CO2 by about 14%, so it was off by about 14% of the observed budget, so it's pretty good. And then importantly, we need to account for methane in these systems because they are a strong source of methane to the atmosphere. And this is a really similar figure, but now we're showing methane on the top in milligrams of methane carbon per meter squared per day. And you can see that there's a lot of positive fluxes of methane to the atmosphere, particularly during the growing season. So this is when plants are photosynthesizing and actively exchanging gas with the atmosphere. And the observations, the eddy covariance measurements are the orange dots, and the model with 90% confidence intervals are in gray. And again, I'm showing the water table height on the bottom, and you can really see how water table height, changes in water table height can really affect both the timing and the magnitude of methane emissions from the wetland. So having that water table lowered frequently during the growing season of 2013 led to overall lower fluxes of methane to the atmosphere. So that's something that the model accounts for very well. Okay, and so now moving on to some performance statistics for methane, we're explaining about 65% of the variance of methane flux that we observed. And now if you look at the cumulative methane over time graph, you can see again it's just this very clear source of methane to the atmosphere, so positive fluxes. And the observations are in black, model is in gray, and you can see during our validation year we were really spot on. So we're estimates for methane emissions were very rigorous. Okay, so overall the model performance is strong, at least in the this restored wetland inside the delta, and we're going to be expanding the model to other types of wetlands and testing it on different islands in the delta. But as of right now, CO2 and methane modeled annual budgets were within 14 and 1% of the measured budget, so it's pretty accurate. Also, the model estimates soil accretion. And so across that time period of 2012 to 2014, we estimated an average accretion of 3.3 centimeters per year. And if you look back at historical data collected by Miller et al. In that exact same wetland from 1997 to 2005, they measured an average accretion rate of 3.1 centimeters per year. So I think we're doing a pretty good job on that front as well, but this is something we're going to be spending more time looking at in the future, benchmarking the model against soil accretion rates as well. And so the model is, it's actually being reviewed right now for a publication in Global Change Biology. It should be published soon. And it's, the model itself is publicly available on GitHub, and we'll be working on trying to make this more and more user-friendly over time, and testing it in lots of different field sites. So with that, I will give it back to Steve. And
Thank you, Patty. I'm going to briefly walk through the steps that a project proponent would take on during the development of a project under this methodology. Before the project start, there are 10 steps that proponent would engage in. They're listed here: identification of the project baseline, definition of project boundaries, legal requirement and performance standard evaluation, development of a monitoring plan, estimation of baseline carbon stock changes and greenhouse gas emissions. Those would all be completed during the ex ante or pre-project condition or period. And then steps 6 through 10 would be also completed during that pre-project time period, but also completed after the project has been developed. So it would involve estimation of project carbon stock changes and greenhouse gas emissions, estimation of the total net greenhouse gas emission reductions, so basically project minus baseline, and leakage, calculation of uncertainty, assessment of reversal or termination risk, and then calculation of emissions reduction tons, which of course is the tradable commodity through the carbon registry. I'll be, in the next few slides, as they come up, I will be talking about actual implementation of these steps, what's entailed in each step, and then walk through an example as the next slide comes up. There we go. So identification of the baseline activity is pretty straightforward. For example, agricultural land in Sacramento-San Joaquin Valley, or Sacramento-San Joaquin Delta, pardon me. The project area must be in agriculture for 6 out of 10 years prior to the project start date. It can be fallow for a maximum of 2 years prior to the start date. The project boundaries, it's required that the project proponents define the boundaries using GIS and provide a shapefile. The carbon pools and carbon stocks are carbon pools for the carbon stocks and greenhouse gas emissions are also to be defined in this step. That's primarily soil organic matter, carbon dioxide, and methane. There's also the opportunity to create project stratification. For example, in a managed wetland, we might have vegetated areas and non-vegetated areas or open water. Within the vegetated areas, there might be areas with varying depth to water or areas with varying soil organic carbon content, which would influence the baseline greenhouse gas emissions. And then there's also the leakage aspect that's included in step 2. I'm going to talk a little bit about leakage because it's relevant to the agricultural situation in the Sacramento-San Joaquin Delta. It's really an increase in greenhouse gas emissions outside the project boundaries due to the project action. So it occurs when land uses resulting in baseline emissions move outside the project boundary, and it's transmitted through market forces. So the change in global warming potential needs to be accounted for as a result of these market forces. And really, from our point of view, the only market affects leakage would result from a replacement of crops by wetlands or rice. We actually conducted a leakage analysis as part of this methodology development. We worked with Duncan McEwen and others affiliated with University of California, Davis Agricultural and Resource Economics Department. We used a statewide economic model and results of greenhouse gas modeling and data collection that's been done throughout the state as part of work in collaboration with the California Energy Commission. UC Davis and others have been involved in that work as well. We analyzed basically 4 scenarios. So we took 35,000 acres of crops and converted them either to rice or wetlands, and took 10,000 acres of pasture and replaced those by rice or wetlands as well. And we basically concluded as a result of this analysis, and it's documented as part of the methodology, it's in the appendices, that the range of global warming potential changes that would occur by transfer or some change in the crop mix that would occur outside of the delta is insignificant relative to baseline emissions. So at this point, having gone through those initial steps, I wanted to walk through an example project implementation of the methodology. It actually is based in reality, but we really haven't, of course, implemented the methodology because it's not approved yet. But there have been wetlands constructed on agricultural lands in the Sacramento-San Joaquin Delta that facilitate the demonstration of how these steps would work. So this Twitchell Island is located here in the western delta. Patty's talked about this island a little bit already. This central area here is where that wetland that was built in 1997 is. This is actually a 2011 photo, Google Earth photo, which shows the agriculture in on Twitchell Island. This is an aerial view that shows the the San Joaquin River here, and the old established wetland that Patty modeled is here. The West Pond is this area here. This tree in the horizon is what we call the lunch tree. That's where we used to eat our lunch on Twitchell Island when we did field work out there. And here's the elevation map. So you can see it's kind of bowl-shaped. The deepest elevations illustrated by this dark blue and purple, which are -7 to -6 meters below sea level. And so before one would start the project, one would, of course, walk through the first 10 steps: identification of the project activity baseline, definition of project boundaries, legal requirement tests and performance standard evaluation, development of a monitoring plan, estimation of baseline carbon stock changes, greenhouse gas emissions, estimation of project carbon stock changes and greenhouse gas emissions, estimation of total net greenhouse gas emission reductions, calculation of uncertainty, assessment of reversal and termination risk, and calculation of emission reduction tons. So in this particular example, the project proponent demonstrates, or can easily demonstrate, the project area has been used for agriculture for at least 6 of 10 years using aerial photos or equivalent. Can, of course, provide a GIS shapefile. Carbon pools are identified primarily as soil organic carbon, and then carbon dioxide and methane. The stratification can be, as I mentioned earlier, basically vegetated and non-vegetated areas. The leakage is assumed to be equal to 0. So this is a map of Twitchell and Sherman Island, which is to the west of Twitchell Island, and this is the area that actually has been converted to managed wetlands on Twitchell Island. There are other areas, both Twitchell and Sherman are state-owned islands, and so there's been substantial efforts to convert these islands to managed wetlands to reverse the effects of subsidence and stop the greenhouse gas emissions. This area in 2009 was actually a corn growing area, as you can see here, And today, our 2015 photograph is the managed wetlands that have been implemented on about 800 acres on this part of Twitchell Island. Here's the 800 acres overlaid on the elevation map. And so here we are at step 3, performance standard evaluation for additionality. And basically what we have in the methodology is that managed permanently flooded non-tidal wetlands on lands which were formerly in agriculture represent less than 2% of the area where one could develop these wetlands in the Sacramento-San Joaquin Delta. Because it's not common practice, managed non-tidal wetland projects are deemed beyond business as usual and therefore additional. The monitoring plan would include the specific methods for monitoring of carbon stocks and GHG emissions. There would be inclusion of monitoring tasks, data to be collected, model documentation. We do require a peer review publication for any model that would be used to estimate greenhouse gas emissions and carbon stock changes. There would be the necessity for a QA/QC plan, data storage protocol, and some kind of organization chart and parties responsible. So estimation of baseline carbon stock changes in greenhouse gas emissions. Under the ACR standard, this is a forecast of the likely stream of emissions and removals to occur if the project proponent does not implement the project, i.e. the business as usual case. So what we've done is estimate the greenhouse gas emissions, or CO2, emitted from the oxidation of organic soils using our subcalc model. So for this 800 acres, it turns out to be about 7.5 tons of CO2 per acre per year. It decreases slightly over time because of the loss of organic carbon that occurs. We know that subsidence rates have slowed over time because there is this loss of organic carbon that occurs, which causes, in turn, the CO2 emissions to slow down slightly. The reason for that is shown here. Ongoing CO2 emissions slow with time as land subsides and soil organic carbon decreases. So moving on to step 6, there would be an estimation of project carbon stock changes and greenhouse gas emissions. These are some data that have been collected for the wetland on an annual basis using eddy covariance as well as corn and pasture. If you look at the right-hand column, the greenhouse gas budget, of course the positive numbers are a net emission or net source of greenhouse gases, so about 6.6 for pasture, about 8.5 for corn. The young wetland that was recently established on Twitchell Island is a net source, but at a much lower level than the baseline emissions, about 1.7. And then the old wetland that Patty has modeled is a net sink at about 0.66 tons of CO2 equivalents per acre per year. Step 7 is the estimation of total net greenhouse gas emissions. So it's basically what we call the delta C ACRs, the total net greenhouse gas emission reductions in metric tons of CO2 equivalents. That's basically the C actual minus the delta C baseline times 1 minus the leakage. So the C actual is the cumulative total carbon stock changes and greenhouse gas emissions under the project scenario since last reporting period. And then the baseline is the carbon stock changes and greenhouse gas emissions under the baseline scenarios. Leakage is the cumulative total of the carbon stock changes and greenhouse gas emissions due to leakage We're assuming leakage would be 0 in this case. So one could look at it from this standpoint. Basically, this is the net carbon benefit that results from stopping current baseline and sequestering carbon dioxide in a wetland similar to that on Twitchell Island. So the current agricultural emissions, as we showed, were about 8.5 tons of carbon dioxide equivalents per acre per year. The CO2 sequestered by the wetlands was about 5.5 tons of carbon dioxide equivalents per acre per year. There's a methane emissions of about 5.3 tons of carbon dioxide equivalents per acre per year. So the net is this plus this minus this, which is a net of about 9 tons of carbon dioxide equivalents per acre per year. And so this, over time, this is an estimate pre-project or ex-ante estimate, but the tons of CO2 equivalents per year for the project wetlands would go up from about 4,500 to about a maximum of about 6,500 because of that baseline decrease over time, go out to 2065. We're looking at about a little over 6,000 tons of CO2 equivalents per year for the 800-acre wetland. There's an adjustment for uncertainty as per the ACR standard and our uncertainty module, which is modified slightly from the Louisiana modular method. 10% uncertainty is allowed, so basically there's more than 10% uncertainty in the overall cumulative net greenhouse gas emissions reductions, this baseline and project. There's an adjusted C_ACR at any given time, adjusted by the amount of uncertainty, over 10%. Again, if the calculated total project uncertainty as determined in the module, which is X-UNC, is less than or equal to 10%, then no adjustments will be made for uncertainty. There is a requirement for risk assessment. There's have the wetland projects in the Sacramento-San Joaquin Delta and the San Francisco Estuary have the potential for termination of greenhouse gas reductions and removals to be reversed when a project is subject to flooding, erosion, or there are intentional reverses or terminations, such as landowners choosing to discontinue the project before the project minimum term has ended. So the current risk assessment tool basically assesses external and internal and natural risks. Internal risks include project management, financial viability. External risks may include land tenure and political forces. The primary natural termination risk to wetlands is flooding due to sea level rise and/or levee failure in the Sacramento-San Joaquin Delta. There's a current minimum of 10% mitigation required to be contributed to a buffer pool as per the current risk assessment tool. So the calculations might look something like this for step 10, where you would have the actual emission reduction tons is equal to this C_ACR times 1 minus the percent of the carbon credits that would be, or basically the percent of the, or the fraction of project emission reduction tons contributed to a buffer pool. So just going down here for a maximum estimated benefit of 6,500 tons of CO2 equivalents per year and a discount of 10%, the ERT would be just basically 6,500 times 90%, or 5850 tons of CO2 equivalents per year. And then once the project is developed, one would walk through steps 6 through 10 for any given reporting period and estimate and actually use one of these methods, ecovariance, feldspar markers, soil coring, etc., aqueous fluxes, chambers, and model to estimate the actual project carbon stock changes and greenhouse gas emissions, and then walk through the step 7 estimation of cumulative GHG emissions reductions, the uncertainty estimate, the risk assessment in step 9, and then emission reduction tons calculation for the reporting period. So that really concludes what I want to say about the methodology. There, as Lauren mentioned when we first started, there have been a number of people that have contributed and organizations that have contributed to this methodology. There's been funding from the organizations listed here. Writing team members included Kyle Hemis, Patty Oikawa, Jessica Orego from ACR, Sarah Mack from TR Resources, and Lucas Silver from UC Davis. And then there have been technical working group members listed here from various organizations that have reviewed the methodology, provided comments, and we've responded to those comments. And then, of course, Lauren has reviewed the methodology as well and provided comments and helpful suggestions. So thank you.
That's great. Thank you both so much for that really wonderful presentation that covered a lot of information in I think, a pretty useful way. So I wanted to just quickly remind people, if you do have questions, you can simply type that into the question chat box where it'll come through to me, and I can send them on to the appropriate person to provide an answer. I haven't seen any questions come through just yet, but I will ask. We have some time, so maybe what I can do until we do have any questions come through is we can also see if there are any sections that Steve or Patty want to go into more detail about. Okay, so we have one question that just arrived, and it is there a sense of how many credits can be produced by a typical project? Steve, do you want to try to field that one?
Yeah, I could say a little bit about that. Through the example, an 800-acre wetland could produce the level of credits that we've talked about, something on the order of several thousand per year. So over 10 years, that might be, for this particular situation, about 50 or 60,000 emission reduction tons. And if you included the area that we're thinking about in the Delta, tens of thousands of acres eventually that could come into managed wetlands, you can multiply that out. But for any given project, it would be on the order of several hundred acres. We're talking somewhere between 7 to 9 tons, maybe more, depending on where it was implemented. Organic soils make a big difference in terms of how much the baseline emissions are. That's really most of the carbon benefit is the emissions from these organic soils. So if you had higher organic matter soils with higher emissions, you could actually sequester or have a bigger greenhouse gas reduction benefit that might be on the order of over 9 tons per acre per year that I cited earlier. So a typical project, I guess to summarize, a typical project might be several hundred acres, and on a yearly basis per acre, you might see something on the order of 8 to 9 tons of CO2 equivalents per acre per year.
Great. Thank you. Are there any other sections of the methodology, Steve or Patty, for the model? Do you want to go into any more detail since we do have some time? If not, we can certainly close early.
I'm okay. Just now that you're showing the emails, if you guys don't think of questions right now but have some later, feel free to email us, and we'd be happy to get back to you. So.
Great. And as I mentioned earlier, this is, if you have any questions or if you want to provide comments for ways to potentially improve the methodology or make certain aspects clearer, whatever it may be for the public comment period, we do want to hear those. So send those on through the acr@winrock.org email address, and they will be taken into account. Okay, if there are no more questions, then I will close the webinar, and thank you so much both to Steve and Patty, and thank you all for attending.
Thank you. Thank you, Lauren. Thanks, Patty.